Hey everyone, how's it going? Getting set up here. Oh, we're actually pretty much ready to go. We've got a simple plan today. We are going to be going through the Pytorch tutorials. I want to not miss a single thing. We've been going through so many different things in Pytorch, and I do believe that it would be very nice if we continued off from where we left off last year, right? Was it almost a year? Almost, was it 2025? When we did a lot of Pytorch basics. On the Pytorch website, we did Neva's tutorial for the matrix manipulation functions. I want to go through all of these. So this is the get started stuff. We're gonna keep it simple. We're gonna keep it simple. I'm excited. All right, that sounds great, Sarthak. Good to see you. Welcome on in. We're gonna go through the simple basics. So this is we learned the basics. We did the quick start. Now we're gonna go through tensors. We're going to go through the tensors. Yeah, I think it's pretty great. Tensors are a specialized data structure. This is going to be easy stuff. This is like easy. This could be an easy stream. No problems. Nothing to run into. How's it going there, Azzy? So you will start again from basics to pro. Yes, that's the idea. That's the idea. Let's do it. So this is on the Learn the Basics. If you go to Pytorch website, you can go into learning the basics, click get started with Pytorch. You can get the basics here and you just skip ahead to the tensor section. This is what we're gonna be working on today. Hey Torva, good to see you. Welcome on in. Happy Tuesday. We're doing some Pytorch and we're gonna do the basics. We're gonna keep things easy and then we're gonna ratchet it up slowly so we don't miss a single thing. I don't wanna miss anything. So let's get into it. Let's get our terminal going. So this is what we did yesterday. We went through all the different activation functions because I just wanted to kind of see what was available out there. And there's a lot of activation functions. There's quite a few. And as you can see, we saw quite a few here. A lot of different options. And it was great. After being a programmer for 15 years, I have been doubting yourself. Oh no! These streams with no AI are always good. Are they? That's great. Yeah, we're doing no AI. We want to learn it. Well, we're learning how to build AI on the stream, right? Happy energy. Yeah, Sarthak, thank you so much. Appreciate it. Yeah, it's good to hear. Good to hear from you. All right, so we did this yesterday. Looks good. We're going to open up a new file now. We'll say, let's close this one. Then we'll say, what's in this file? Oh, because we got a test already. So we'll say vi tensors.py import torch. What else do we need to do? Oh, import NumPy. Why are we importing NumPy? Torch already has NumPy-like things in it, right? We can already do manipulations mathematically with division, addition, subtraction, concatenation. Remember, we did all that with Nevas. I guess we're going to be using some import NumPy as NP. Really, really important things here, right? At the top of the screen, looking good. How's it going there, Jinlu? Good to see you. I got quite an interesting way to watch the stream today. Are you in VR? Are you in some VR over there? All right, let's see. We're going to get your song going, Jinlu. Whoop. There we go. All right. Getting Jinlu's song going, and then we'll head into the playlist. All right. Let's go here. Let's make sure that this works. Python, and it was called Tensor. Wait, what? Oh, is it not saved? Oh, we didn't save it. Python Tensor. All right, there we go. Python Tensors. There we go. Run. Looks good. Okay, good. No, I got something way more interesting. Do ya? All right, let's check it out. I'm curious. Let me know. I'll send a screenshot and video. All right. Sounds good to me. All right, let's get our data going. So it's very simple data. So data, our input data probably, right? 1, 2. And so this is a batch size of 3 and 4, 3,4. There we go. And hey, how's it going there, Somaya? Good to see you. You're back. Welcome on in. Hi, Stevie B. Hey, Sergio. Thank you. Good to see you. All right, you know what? We also have to do today, you guys. We have some gifted memberships we got to give out. We got to gift some memberships. Don't make me forget. Don't let me forget. We got to gift some memberships. All right, X data. All right, so this is going to convert it to a tensor. Wait, did we say tensor? Torch.tensor data. So this will, so if you print this and then you print X data, it's going to be different. So one is going to be the native Python data in CPU world. This is also in CPU because we haven't sent it to the device yet. Hi, Stevie B. Hey, Tyson, good to see you. Tyson I7G, welcome on in. Good to see you. Hey, Neva, how's it going? Neva, it's so great. It's like, as soon as we start doing Python stuff, you're back again. It's great. It's like you're back again. All right, so tensors. We're doing the basics. So we're gonna start over. It was requested many times that we start from the basics and we go more to advanced. So we're gonna start on the basics, and we're going to go through the actual tutorials on the Torch website. Real Mashy, how's it going there? Welcome on in. Thank you for saying hi. We're walking through some Pytorch today. All right, so NP array, or we're going to convert that to a NumPy array. So we can do NP data equals NumPy. Was it NumPy? No, torch dot from NumPy. Oh, NP.array. Okay. So what do we call this? And yeah, I already did. All right, so this is going to be to NP.array with an extra R data like that. And we can print that as well. And we can see what the difference is. It's different structures there. Whoops. There we go. That was not planned, was it? All right, that's just how it worked out. It wasn't planned. Hey, Brendan, good to see you. Mostly the front end stuff. All right, no worries. Yeah, that's what we were doing for the past month and a half. So I got it. Less on those streams. Understood. Let's do some, non-front end work here. All right, so we got the NumPy version, you've got the Tensor version, and then you've got the native Python array version. Pretty neat. Okay, very basic, very simple. Then you can also capture a tensor from NumPy data. Okay, so this will be x underscore np. NP, this is neat. I've never used this before. I've never done this before. So you say torch.from NumPy? Was it from NumPy? Yeah, it was from NumPy. NP data. There we go. And then that will also, basically these two will be the same. X, so let's go XNP. There we go. Which ID are you using there? This is Vim. You can see here, standard good old Vim. We love you. Oh, thank you. Appreciate it. Or is it notebooks? This is just Vim. It's Vim in the terminal with Tmux and Ghosty. Tmux and Ghosty, you guys. Tmux and the Ghosty. Vim with Tmux. There you go. Tmux Party Popper. And G Hosty with 2 T's. Okay. Leave that. All right. So these two will be identical right here. This one and this one. Those two should be identical, right? So if we look at them, we should see 2 tensors. And they should be captured just fine, just the same. Right, yep, right there. Tensor 1, Tensor 2. Right there. There you go, look at that. All right, we're keeping it simple. Really simple. All right, so let's do some, retains the properties of X data. Oh, does it? Ones like? What? Whoa. Wait, this is weird. All right, I don't know what's going on here. Why would you ever do this? I don't think you would ever want to do this. You'd never want to do this. The Python arrays are a project, so like 32x the size of bunch of random. NumPy and Pytorch are both similar to C representations. Okay. Yeah, I like C. So after learning through the matrix manipulation walkthrough that you put together for us, Neva, what was really powerful that I learned a lot is that you don't need NumPy anymore with Pytorch. Well, for the most part, right? For the most part, obviously, if you're dealing with NumPy data, however, with Torch, you don't really need to import another library here. You don't need that. You can just use native Torch, and it has all the same NumPy functions that you'd want. Plus, it keeps a connected graph, so if you want to put that into a model, you can just copy and paste it right away. That's why I like it. That's why Torch is amazing. Would you like to join defense company like Lockheed Martin? The Lockheed Martin? The Lock H Martin? I'm good for now. I'm more of a constructive, not a destructive. Yes, okay, you got the idea. Easy. Yep, that's it. Getting at it. Yep, we got the idea. All right, let's keep going. All right, so this is weird. X1s. I don't know what this one's like. I've not used that function before, so we're going to learn about this one. Say x underscore ones equals torch dot ones underscore like. Are you serious? That's a function? Why is that a function? Data, x data. Can we do that? All right, so what happens when we print this? X1s. What does that look like? This is weird. What is this? What's going on here? Can you put your TV startup on Discord? Your TV startup. What? Are you talking about like the shared canvas? This thing? This thing? Remember this? The shared canvas? Is TensorFlow not much used now in the industry? It is. Google uses TensorFlow, right? I'm pretty sure, right? Does Google use TensorFlow to Gemini? Let's find out. All right, Google use TensorFlow for Gemini? Question mark. I'm pretty sure they do. It's ones like is the same as doing shape passing to ones. Okay, it's basically a way to get a tensor with all ones of a specific shape. If you think your phone's ringing, it's not you, it's me. Don't worry. Sorry about that. How is stream a cropped screen like yours? Oh, it's like this. So you can see right here, we've got a vertical and a horizontal. Right like that, vertical and horizontal. You see that? You just got two of them at once. That's it, that's how you do it. And then you just put the screen together as thusly. Genuine question, do you know about the company PwC? I know of it. Google uses JAX now for training. Everyone deploys on TensorFlow at least a bit. It says, while Gemini models are built on specialized infrastructure, the two designs are integrated with Google Cloud Ecosystem. All right, optimized for low latency modular. The core architecture Gemini models, which are distinct from the open source TensorFlow. Okay, so you're right. You're right. They might not be using the TensorFlow, the whole different framework that Google created. They're doing something different, apparently. Like Gemini Nano, formerly TensorFlow Lite okay, so they're some sort of evolve. You said JAX. Many new models are being developed using JAX, while TensorFlow continues to be a key part of their production and enterprise integration strategy. So they're using JAX now. You called it. Never, you're right. Google named their phone processors Tensor. They did, Jinlu. You know that part at least? Yep. They also have TPUs, Tensor Processor Units, which are essentially accelerators or like ASICs, specifically designed for matrix multiplication. Not showing any other tabs. Which ones you receive startup, you can put a video on Discord of it turning on. Oh, Brandon got it. Okay. Understood. You're talking about something else. Yeah, you're talking about not what I was thinking about whatsoever. So yeah, would you deploy code not on Python? You would do deploy code, just not on Python. Got it. A friend is working on something middle layer called Stability. Stability. That sounds great. Tell us more about it. Put a link on Discord to support TPU and building drivers using JAX. Oh, very nice. Now we're getting into it. Let's see what this does. I'm curious about this. I want to see right here. All right, save, run. All right, what does that do? Oh, it just that's all it does. I mean, come on, really? So it takes the original input, finds the shape, and then creates a new array, or a tensor in this case. They're the same thing, a new matrix with all filled in ones, right? All filled in ones. Can we do it with other data? Can we just say data straight up like that? I think that'll work too, right? Oh, it doesn't like that. It's got to be a tensor. Okay. All right, fine. Talking about Google, you got it. That's what we're doing. Oh, that's cool. Like TPUs is such a weird thing. It is. It's pretty neat. I think it's great. Accelerator for a very ASIC, application-specific accelerator. All right, let's keep going. Let's look at the next thing. All right, so we're learning little bits at a time here, you guys. Little bits at a time, and then we'll eventually build something. We'll eventually build something with a random constant of value. Oh, we didn't do rand. Okay, like rand. So this is identical to the one above, except for this will give us a bunch of randoms. All right, clear that screen. Looks good. Okay, so this will be x underscore rand. Did we do that? X rand? Yeah. Equals torch dot rand like. Was that right? Did I get that right? X underscore data. And then we print x underscore rand. Let's see if I got it right. Did I get it right? Hey, I didn't get it right. What did I do wrong? Oh, we gotta do a D-type. D-type equals torch.float32. Is that better now? Is that better? I think so. Let's try it again. The Intel wasn't losing so badly. All right, the poor Intel. The AI race, they would have been cool to have Intel hardware to play with the people it actually developed for. That would be great. Check the OG canvas made the one. All right, Brandon, we'll check the OG canvas. We didn't add the history to it, so I think it was called, what was that called? Let's see, here it is. All right. Let's see if we got it up here. Canvas right here. Did we made it work, right? So this will be HTML shared canvas. All right, I got to construct the URL. 1 second. We're constructing the URL. 1 moment. IO. Dot go. / canvas. Canvas. There you go. All right, Brandon, there it is. Hey, what GPU do you have? All right, we have a integrated GPU. It's not that, it's an integrated GPU. It's not like a fancy NVIDIA or anything. 157778. It's just a regular one. Not a lot of code made for Intel stuff. I know, Neva, that's right. This sound hits nostalgia like it does old YouTube videos. All right, that's an old YouTube. We got some old YouTube songs. That's some YouTube playlist stuff here. Got some YouTube playlist stuff. All right. You're afraid in remembering so much of syntax, each language and each framework has something different and different parameters. It sure does. The good news is you only really need to memorize the patterns. You can always look up the documentation later, right? That's what I do. Always look up the docs later. You just need to know what's possible and what doesn't work and what will fail. I think that's a really good one. Math used to be so much fun, did it? It's not fun anymore. What are you talking about? Why isn't it fun? What'd you lose? I wrote chair on the canvas, did you? Hey, you sure did. It's chair. Do you remember, Brandon, the other stream where someone was writing, someone wrote T right here? There was a short, they wrote T, and then they kept erasing your R. They kept erasing your R. Do you remember that? I didn't even notice it. I didn't even notice that happening. And then you kept rewriting it. You're like, you rewrote chair. You're like writing the word chair. And then someone like erased it again. They're like, no, chair. And they erased it again. And then they wrote T again. I thought that was funny. All right. Getting back to it. We got to get back to our code now. All right. So this does random. Can we do not float 32? You always want floated. What if you float 16? What if you do float 16? Is it going to make a difference? Is that going to even work? It sure does. What about float 4? Can you do float 4? Let's jump to the bottom. Oh, too low. It's too small. What about float 8? Can we do float 8? Nope. All right, 16 is the minimum. 16 is the minimum. Yeah. All right, let's get back to our HTML goodness here. Let me pin this tab so we always have it. All right. Also, let me go back. Where was that at? Here? Yes, let's bring this back here. All right. Pin that as well. Looking good. Okay. Yeah, at least prices got take a little bit. What are you talking about? Specific rate platform and then something walled and CPU. Oh, the prices got something. Can you try bfloat? Does your hardware support bfloat? We're gonna find out. Bfloat. What is this? What is that? What is bfloat? I don't know what that is. We're gonna find out. Apparently, no. Torch doesn't have attribute bfloat. I don't know if that's. I don't think that's a me problem. I don't think it's a me problem, Torva. Neva. I don't think that is. What does your setup look like? Hardware and software for streaming? It's a Mac. It's a Mac, right? You name. You got a Mac right there. Right there. Mac right there. Which window manager are you using? The native Mac window manager. Ordinary window manager, and we're using what you call OBS, Open Broadcast Studio. That's it. That's all we're doing. It's super easy. Nothing special or fancy there. All right. B float 16. Okay, thank you. All right, let's find out. What's B float 16? We're gonna find out, you guys. What is this? What is it? What do you think it is? Is it? It's just a regular float. We're gonna find out if it's gonna look different or not. All right. Hey, sure does. Look at that. B float 16. What I know that was. What is the difference? B float is the same. Is a thing made for AI, specifically huge models, for the real big ones. What does it do? What does it do? Let's find out. We're gonna find out. All right. Pytorch B float 16 versus float 16. Let's learn. Let's learn together, you guys. The primary difference between the B float 16 and float 16 is how they balance range and precision. But I just call it a different precision because it's 16 bits. Has a wider dynamic range, while float 32, but less precision. Yeah, well, yeah. Hold on. Wait. This doesn't make any sense. Mantissa bits. Exponent. Oh, reserved bits. Got it. Okay, so when you construct some sort of value in memory, you're assigning a number of bits to it. A number of bits. I got it. Okay. So let's graph this out so we can see what's going on here. Let's graph this out. Is there like a dark mode? Here it is, dark mode. All right. Let's clear the canvas. Let's learn this together, you guys. Let's clear this. All right, so we want to clear the entire canvas. Where's that? Extra follow precision. Where is it? It's open, save, export, command, find, help, reset the canvas. It was right there. Okay. So let's do this. Let's draw together, you guys. Let's learn what the difference between a B float 16 is and a standard float 16. It's a float with moving stuff from the mantis to the exponent. B floats are less likely to overflow because they've got more in the one of the sides of the things that are used more. Okay. Let's learn it. Okay. Where'd that at? Where'd that go? Where did we put it? Is it over here? Here it is. Okay. Nice. There we go. Music got intense there for a second. Where is it? Where did we put it? Right here? Okay. Let's move this over here. All right, got a little bit calm now. All right, you guys. So let's take a look here. Difference between the floats. So total bits. So let's bring our bits out here. All right, so we're gonna say. So this will be a line, and this will be another line. Oh wait, number 6. We'll do another line. Okay. One line is going to be 8. This will be B float 16. The other is going to be a standard float. Just a float 16. Okay. Let's look at the difference between how these two are constructed. Yes, basically has a huge massive swings in size. We don't care as much about the value beyond the order of magnitude. That makes sense because you only need so much precision. So it makes sense to change how we use numbers. Yeah, I agree. It sure does. Intel hardware, likely the B float, it goes vroom. It does in Intel. Okay. All right, sign bits. Everybody has one sign bit. Okay. So let's do that. We get 1 bit for the sign. This will be positive/negative. Or, well, maybe we can make that a little bit. There we go. So we get 1 bit for that. So we both get that. We get a sign, right? There's 1 bit. And then how many bits do we get for? Thank you for the hearts, you guys. Alex, good to see you. Welcome on in. Hey, what are we doing today? I try hard. Good to see you. Thank you for the floaty heart icons and reactions, you guys. We're booing for the Pytorch. We're going over the Pytorch. Never brought up a really interesting concept that I've not ever used a B float before. A brain float. Oh, brain float. More in the exponent bits, less in the mantissa bits. Precision lower, precision higher. Interesting. Oh, interesting. Okay, so it actually reduces the precision. That's not what I was thinking. I wasn't thinking that. Thank you for the hearts, you guys. So yeah, it's X sine mantis 2 exponent. X's. Got it. Okay. What is the mantis? What is this? What are the bits? I need to know about this. They're just bits, so it's the mantissa bits or significant bits represent the fractional significant digital of a floating point number in computer science, determining its precision. Oh, all right. Okay, perfect. Well, so that's where all the main data is, and what they are stored as normal binary fractions, usually 23 bits for a single precision and 52 bits for a double precision, with an implicit leading 1. Oh yeah, I was just double checking there. All right, making sure our music's right. Got to make sure the music's right so we don't hit any what do you call it? Copyrights. Interesting, you should try running some small LLMs on your machine and quantize some to use B-floats for quantization. Hey, there you go. A little bit faster. You're pronouncing it wrong. It's called mantissa. Oh, mantissa. All right. I was calling it something different. The mantissa. All right. It doesn't look like it would be, but I guess it is. Almost got the video. Sounds good, Jinlu. We'll check that out. So pronounce mantissa. The A is not an E. It sounds an A. So mantisse. Yes, English is not. Yeah, exactly. All right. Well, let's do this. Translate. Detect.
Mantissa.
Mantissa.
Mantissa. Mantissa. Mantissa. Mantissa.
Mantissa. All right, we got mantissa, you guys. The mantissa bits. I didn't know there was a thing like that. I never needed to use it before. All right, where are we at here? Where to go? Is it right here? All right, I'm gonna pin this so that way I know it's really right there. Okay. Check your general now. All right, Jinlu, let's check it. We're gonna see the mantissa bits. We're gonna pull this together so we can learn together, you guys. The mantissa bits. Oh, we got some Minecraft going on here. Oh, no way. Check that out. I was like, I hear myself going, you've got a video screen in Minecraft and you're typing in chat at the same time? Are you kidding? Yeah. Look at that. Oh, that was amazing. Mantissa. That was great. Jinlu, wow. Oh, look at that. I didn't know you could do that. It's mostly, you want to quantize the B-floats. It's for training. It's mostly useful for values all over the place. Smaller models don't gain much from it. Makes sense because you just don't, because everything's spread out in the large models and you just don't need that level of precision. You don't. Also, depending on hardware, it's faster to run. It sure is. It sure is. Less bits, faster. Makes sense. Why my Samsung TV has the goofy startup. It's the 2007 model. It does? Wait, Brandon, I didn't know about that. I don't know. When you boot it, it's got an interesting on-screen startup. That's how I'm watching. That's how I'm watching right now. Jinlu, that's great. That is amazing. So you can be in Minecraft and you can just go over and look at the computer screen in your Minecraft world. That's impressive. The other thing you saw on the wall a bit earlier was a clock. I saw, it was a web page. I saw a clock. Where is that? Yeah, right here. This right here, Jinlu. Multiplication of B-floats is less actual multiplication to do, so it's mostly addition. Oh, we're learning more. B-floats, you guys. We want to use the B-floats. Do take some on quantization as well. Do take something on quantization. Yeah, quantization, my understanding, really, they take an existing model, the full model, you load it into memory. Instead of loading every single bit, you truncate the bits, right? You truncate the bits. That's it. So you can reduce the model memory load requirement by 50%. If you do that, you can reduce it. So that means it allows you to run larger models on smaller hardware. It's rare, Samsung LCD Slim TV with a startup. It is. It's back in 2007, the TV would just turn on. If you got an emblem, you were special. Smaller models don't gain much. machine learning, a lot of parameters in order to experiment with quantization. A small model can be used. I try hard. We're learning together. That's great. Thank you for this, for the details. Keep them coming, you guys. Keep them coming. Yeah, it's a web page. Nice. That's awesome. All right, let's keep going. Let's keep going. Okay. Yeah, that's a web page. That's neat. It was neat with images. You have no general idea, but you're missing soul steps. No, you have the general idea. Oh, got it. Got it. We're missing some steps. Understood. The song is copyrighted. Uh-oh. Let's see here.
This is not a test.
Let me, you know what? Yep. We'll have to fix that later. See, licensed apply. Okay. All right. So now I got it there. Vocals, instrument only, apply. I'm getting the music. I'm getting the music back, you guys. All right. There we go. Does that look about right? That like made it a really small, tiny. Okay. We'll deal with it. We'll deal with it later. Okay, let's keep going. Hi, what's up? Hey, Mitchell's. Welcome on in. Good to see you. Happy Tuesday. Quantification. You first take a model and figure out the max and min values each neuron does by running on the same data. So you need to figure out what the I thought you could just decide up front what you want the quantization to be. You can decide what is the minimum when you're loading it. Then you basically move from float to integer arithmetic. Oh, you do? Okay, integers at least on the CPU are faster by a factor of 4. Really? You want to watch your stream more often? Oh, but the time zone differences make it tough. Yeah, I'm usually go live earlier in the day. We have a lot of early meetings next couple of weeks, so we're going later in the day. We will go back to early morning. We will. I try hard. Thank you for stopping by. Good to see you. And you also need less memory because you already encoded the scale statically. Nice. Got a question. If a viewer comes to your house and then they want to sit in your chair, would you let them? I remember you asking that, Brandon. I thought about that. I remember you talking about that previously. I thought about it. I know what you're describing. It's. I remember you asking that question previously. All right, so let's get back to. I wanted to see what this is going on over here. So we've got our sign bit. We've got an exponent bit. So we'll go this. We'll say exponent bit. How do we represent this? Exponent bit. EXP bits. So that's 8. There's 8 of them in the B float. Okay. 8 EXP. 8 EXP bits. And then how many EXP bits do we have in float 16? Only 5. So there's only 5, so we can shrink this down to sort of represent what 5 looks like. 5. I'll make that a little bit bigger. All right, so there's 8 there. Okay. And then the mantissa, or was it mantissa? I forgot already. Mantissa. It was mantissa. All right. Is it done for today? Oh, we're still going. When can we expect the next stream and lineup agenda? So we are going to be doing more Pytorch. We're going to be walking through the tutorials, and I want to go through essentially every tutorial. I don't want to miss a single thing, because I've been using a lot of frameworks over the years. I've been using my own code from scratch. The frameworks, it's pretty easy to miss something on. Hey, Broth, good to see you. Thanks for saying hi. Hi, Steven. Good to see you. Basically, scale float 33, data int tensor. So you can, from a float to an integer. So you just you move the decimal up and then you lop off anything remaining. Is that how that works? You just change the decimal around? I'm assuming. All right, let's keep going. So let's look at this. All right, then we've got the mantissa, which is weird. I'm still not familiar with that. We got the mantissa here. All right. So we got our mantissa bits. Mantissa, which is going to be 7 in the B float. 7 mantissa bits. And knock knock, who's there? Can someone share the Discord channel link, please? Oh, yeah, absolutely. Just for you, since you're asking. Well, also, it is in the link tree at Sarth. Here we go. There you go. Discord link just for you. Just for you there. Would you like to check my latest output in YouTube AI script? Yeah, I would. I developed my own AI and want to try to make it work in different branches. Right now, focusing on automating YouTube Shorts. Hey, Mitchell, yeah, Mitchell, yes. That would be great. Send it over in Discord. Send a link in Discord. You basically move the decimal point. By scale, and then you round down. All right. There is something with how overflows are handled. There's also an overflow. Got it. Stephen who? All right. Let's see if we can finish this diagram. We're just trying. Oh, we got 7 versus 10. Okay. All right. So a regular float has 10 mantissa bits. 10. There we go. What are you doing automating YouTube Shorts? Yeah, that's a good question. So there we go. So we did it 1, 2, 3. So there's 3 options. Okay. And they all have 16. 8, 9. Yep. So this is 16 here. And this is also 16. Okay. 16 and 16. So did we get this right? So there's 1 here. All right. So this gives us what that looks like. B float versus a standard float 16. So if we zoom in on this, we see we've got our bit or sign bit. Then we've got the float 16. Was it double? Let's double check. Float 6. Yep. 5 and 10, right? 5 and 10. 5 exponent and 10 mantissa bits. The mantissa bits, from my understanding, are representing the fraction, is the actual data. What are the exponent bits? Why are we not having side-by-side view and stream? What do you mean? The view is small for the screen. What's side-by-side view? Zoom is helpful? Oh, are you talking about horizontal? You want some horizontal? There is a horizontal on Twitch. We got horizontal going on Twitch. So you can see the side-by-side view here. Right here. Side-by-side view. My system learn what is in viral and try to... Oh, all right, Mitcha, got understood. Your YouTube Shorts generator will understand what will be the most likely to receive a lot of interaction. Stephen Hocodes 24/7. Oh, that's who. All right, Brandon, I gotcha. Knock knock. Who's there? Stephen who? Stephen who codes 24/7. Well, you could kind of count that if you're thinking about if you're coding in head. Mantissa bits are determined floating point numbers are determine a floating point number precision and accuracy. The actual digits, while exponent bits define its range and magnitude. The scale by controlling the binary position. Oh, together they are sign bits. Oh, got it. So if you want a very large number, you can have a very large number and a small number at the same time. Got it. However, in AI world, you always have very small numbers. You usually never have very big numbers. Usually. You won't quantize in Pytorch. Generally, you would take some code already made for it, and there are just some deployment-oriented stuff. Did an open Vino cause Intel? It's very good. It's very good. The open Vino and Intel. Check the original shared canvas. All right, the original. Hey, is that right here? I see it says Minecraft. You wrote some Minecraft right there, Jinlu. Wait, did you do that in game? Did you do that inside Minecraft? You probably did that inside of Minecraft, didn't you? I think you did. Yeah, YouTube gives a lot of info which wasn't available right now. It gives access to AI and helps learn. Oh, Mitcha, good to know. Good to know. Jinlu, you probably wrote this in Minecraft, didn't you? All right, let's get back to the tutorial. Yeah, you tried writing it in Minecraft. Yay, look, you did. That's actually really good. You did a good job. Screenshots in general. I want to see how you did that. Nice. Take a look at that. Now you're in 3D world and you've got the screen and chat all at the same time. No opposite. B floats is less accurate. Right. I understood that part. Larger and smaller numbers. Got it. So you can support larger numbers and smaller numbers at the same time with the B float. So that way it reduces the precision for the mantissa bits. So it's lower, you have lower resolution small numbers. Large is actually more intrendating. What? Intreading. What is that a word? Can you search the TV with the goofy startup? It's a Samsung. I'm actually kind of curious about that. I'm curious about that copy. Images. This right here. That right there. It's cool because it's technically just projecting a Chrome output onto the game, is it? Nice. Yeah, that is really neat. I'm satisfied with this. This is really satisfying to see. It's really, because in Minecraft, I've always ever, put blocks down to see like real other stuff. Sorry, on phone, hard to spell. Oh, interesting. Got it. All right, I figured it out. Understood. Large is actually more interesting. Good to know. Okay, let's get back into our tutorial, guys. So we learned about the mantissa bits and the exponent bits. Exponent bits for large numbers. Mantissa bits, resolution for small numbers. Precision for small numbers. Right? And so it's just slightly different between the two. No with white one. Oh. This one? Well, I don't know if there's much on it. That's all we got. We don't have anything else. The power of modded Minecraft. Yeah, exactly. All right, let's keep going, you guys. I want to keep going on this tutorial here. We have some time, not a lot of time though. Okay. So let's do some more tensors here. Shape 2-3. Brandon, yes, nice. All right, we found it. So let us just comment these really quick because we don't need them anymore. Okay. All right. Shape is we're going to have a 2,3. Tuple. Nice little tuple there. Then we're going to make a random tensor. So let's call this rand tensor. Torch.rand. And we put shape in here. Like that? Just like that? Yep. Okay. We print rand tensor. Here we go. Okay. Off to the races. Okay. Yep, that makes sense. So it's a 2x3 matrix randomized. So there's other options. There's ones and zeros. Ones. Tensor equals torch.ones. Shape. You also have zeros. Like that. Tensor. Did I really not show ones like? Oh, we did. You did? Oh, we showed it. It's up here, right? Take a look. Right here. Right there. One's like. Right there on the screen, Neva. We did. We showed it. It looks good. It's understandable. Essentially, it just takes the shape of the input tensor and it recreates a new tensor, all filled with ones. Ones like. Which is weird that they have a function like that, because you could just grab the shape and you could do the same thing, right? So you could say, what is it? Ones like, so you just say, right, what you do is, ones x underscore ones equals torch dot ones like, and then you say x underscore data, and you set shape. You don't, yeah, I mean, or you could just say ones like this, right? I'm pretty sure there's the same between the two. Ones like, so here, like this. These are identical. These two are the same. They're the same. Hi, how's it going there? Jalik Patterson, good to see you. Welcome on in. Just use AI to learn to code. It will naturally teach you to learn to code with math. Will it? With math, it will? You mean the last stream where we went over... Oh! Did you? I don't remember. Probably? You probably did. You probably did. I don't know if we did ones like... I feel like maybe we did. You know what? I just forgot. I completely forgot. It's been a while. Hey, Kyle, good to see you. Welcome on in. Like we're doing a rehash. Yeah, pretty much. Because we were stuck in front-end world for the past half of a month. Stream. We probably did. My TV takes too long. Takes a PC power supply. Oh yeah, I know what you're talking about. Those cables. I didn't know if I had. So it's not. Hey, it's all good. It's all good. We could validate that. Where was that? Where was that? I don't remember. It's somewhere in Discord. We'd have to find it again. If you have the link, we can go and validate it. Although we have it on our desktop, don't we? We might have it on our desktop. Let me find out. All right, let's go Pytorch. Let's look around. Let's look around here, you guys. All right, Tmux. Go ls. Where is this? It's probably under cd. Pytorch? Yeah, there it is. Pytorch. Pyto. And then cd tutorial. Where is this at? I'm just looking through stuff, you guys. Where do we put that? No, not this one. cd python. Basics? Yeah, Python basics. Yes, Pytorch guide. Okay, cd Pytorch guide. All right, grep. All right, so it's in here. It's in here somewhere. We're gonna find out, guys. We're gonna find out. Check your last vid comments. Which one? There's a lot of last vids. It's like prompting and getting quick answers and watching shorts. Oh, nice. Okay, we're learning a little bit more about what you built there. Did you hear Claude got hacked by Claude from a Chinese attacker group? All they did was a basic lie. And all they did was a basic lie? Are you serious, Kyle? Really? That happened? Share the link, please. I want to see this too. I want to see it too. All right. So it is around here somewhere, isn't it? Let's do a grep ones like star. Grep dot. Grep dash I star. Skills is a directory. Oh, it's not here. Okay. Yeah. All right. One's like apparently never. No, I haven't. You should add it. Yeah, you should. I mean, it's okay that you didn't because why would you ever need to use it? You never need to use that one. All right, we'll close that out. Close. Actually, wait. Whatever. Okay. Yes, Kyle, that would be very interesting to see. Okay, so these are the same. These are the same. No, wait. These are the same. Right here. These would be the same. Data, X data. I want to double check that. Rent X. Okay. Let's see this. Python tensors. Yeah, they're identical. They are identical-ish. They are different because this one takes the same data type. This one generates a float. This one is an integer. So they were similar. They are similar. I could see why you would want to use them differently. Ones or ones like. The likeness includes copying not only the shape, it also copies the type. D type equals. Can we do int? Yeah. So there you go. Yes. It's actually nice for simple stuff since the baseline STD is 1. So the simple stuff, there you go. I've always used random. Isn't it interesting? I've always used random. I wonder, it's probably fine that you could use anything else. Like I've always used, whenever initializing an array in an AI application, I always randomize the numbers. I always found really good outcomes by doing that. especially when writing my own models, my own framework from scratch. All right, let's keep going, you guys. Let's keep going. All right, so zeros. We can get the zeros in there as well. Up, up, up. All right, zeros. Underscore tensor. Equals torch dot zeros. Was it zeros? Zeros. It's actually hey, how's it going there, Sky? Good to see you. Welcome on in. Happy Tuesday. Shape. All right, Python tensors. Did we not print that out? All right, print. Okay. Zeros. Let's take a peek at what that looks like. Some little 2x3s in there. A little bit of 2x3s. All right, we got our zeros, we got our ones, and we got our randoms. Check the vids comments you made yesterday. The vids comments. Oh, whoa. Oh, whoa. Jinlu, are you doing this? What's going on here? What's happening? This is the, whoa. It kind of looks like, what do you call it? Subnautica. Looks like Subnautica. Brandon, the vid comments, which are you describing of thusly? All right, let's pin this one as well. So we have that one there for memory. This is getting crazy. How you all protect your eyes from such screen exposure, like using retina display for extended monitor as well? No, that's not you. It's kind of cool though, isn't it? All right, I don't know what something's going on there. Oh, is it a watch? It's a watch. It's a fancy watch, you guys. It's a fancy watch. The one you made the other day. I made a lot the other day. I made a lot. I made so many. Like over 10. Over 10. The one you made yesterday. I made 10 yesterday. I made 10. I'll try to find it. Let's see. The challenge is that there's just too many. There's just too many. So there's just too many for me to look through. I'll show you. There's just too many. I can scroll through them. There's just a lot. I can keep going. It says of about 762. It's actually thousands. It's actually thousands. The live? Okay, let's see. It's going live. All right. So yesterday's live. Okay. All right, that's it. We're done. There's nothing there. There's no comments or anything. What's going on? Watch with the watch. Is this a game? This is. I don't think it's a game. I think it just looks like a fancy watch. I think just like a fancy watch. Steven, would you want a tutorial over something else to do with AI? Let me know. Yes, I do. I do. Because I make a particular easy one we can make. That would be great. Right now we're going through the website introductions. For those who are asking about it, they said, hey, we should probably walk through the intros. We should probably do the intros. I said, okay, let's do the intros. This is looking great. All right, we're going to leave that going there. So let's keep going. So we've got these outputs. Looks good. Attributes of a tensor. Tensor, we can get the shape, the type, and the device. Okay, let's check this out. So let's go print. We go zeros. Let's do the random. Nah, we'll do the ones. I like the ones better because it feels like there's something in there. There's something there. When you put a TV startup on Discord. I don't remember, Brandon. I really don't. I know it happened yesterday. It was like, how could you possibly not remember? My day was filled with a lot of stuff. What are you LP extractor? What are you LP extractor for logs? Hey Zane, hey Zany, how's it going there? Good to see you. Welcome on in. Happy to have you here. ULP extractor. Let's look this up. ULP extractor. What's going on there? Universal extractor tool designed to extract files from any executable. Oh, yeah. What do you want to do with that? What are you trying to do? Are you trying to do something malicious? What, or something constructive? I don't know. What are you trying to design to extract files from any type of executable? Yeah, I don't know. Usually when something's built into an executable, they kind of, the author, the original developer kind of intended that to stay inside the executable. They don't want you to go sneaking in there. How's it going, Mark Lemon? Good to see you. Thank you for saying hello. What do you think of the idea about code optimization agent to optimize large code bases and each individual function with good benchmarking? Optimizing is hard. Agents tend to write badly optimized code. My experience, Neva, with the latest models, they're actually pretty good. You have to give them very specific tasks on what to optimize. You can't just give them blanket optimization. You have to say, I want you to optimize this specifically right here. Look at this. What needs to be improved? And it comes up with a bunch of ideas, and you can pick like 2 of them, and it works really well. You got the logs? You did, Zany? Nice. It makes sense if your devs raw worse than the average agent. Yes, if they are worse than the average agent, then it does work better most of the time. No, like when you put a TV startup on Discord, I want to see when you can put one. I don't know. Hey Nathan, Minecraft, good to see you. Welcome on in. Brandon, I'm really trying to remember. I'm not working out today from the memory. Yeah, although you can sometimes optimize very specific processes if you already have an idea how to optimize it. Yes, Torva, there you go. That's usually what I do. So I usually guide an AI to sort of do kind of what I would be doing anyway. And it does a very good job. Hi, since when are you in the coding industry? Oh, all right. For those of you who are new here, I'll answer you some questions if you jump over to my LinkedIn, y'all guys. My name is Stephen Blum, CTO. We are a API company that has 1 billion devices connected to our network. 68 patent claims granted. 25 years in tech. Because you asked, Uday Gupta, since you asked, been 25 years professionally in tech. Obviously been doing tech longer than that. I've been coding longer than that. Just from a professional perspective, it's been 25 years. Yeah, exactly. You need to be realistic, really specific. Yeah, you do. Do you know about Silver Bullet? I know of a Silver Bullet. Thank you for the hearts, you guys. Appreciate it. Yeah, exactly. You need to be really... I'm just better at the average agent optimizing Rust, so usually you're not... Oh, got it, Neva. You yourself are able to outpace the AIs. Like having an agent go look at the profiling, it gave a specific ABC needs to happen. I usually get pretty good results. However, sometimes it goes the wrong direction. It tries to optimize it in a way that does not necessary at all, which essentially adds overhead. I've seen that happen before. Hey Farzi, good to see you. Hello again, Steven. Just go optimize on a large code base. Yeah, exactly. That won't work. Yeah, you have to say, you need to optimize this function right here, make this faster. What needs to happen? You're right. What did we do here? What were we doing? Where were we at? Oh, we were going to say ones like shape. Then we had something else. We had dtype. And we also had another thing, which was, let's see if we can remember it. I got a joke on your TV OS. Hungry because it made in Hungary. Ah, the Hungary TVs are hungry. What are you up to? You deleted it, Brandon. Why'd you do that? Farzi, what are you up to today? Oh, we're building ourselves a Pytorch tutorial that we're actually walking through the Pytorch tutorial. That's what we're doing. It was called Device. That's what it was. Device. So we're walking through it right now, and we're getting up to speed again on Pytorch. Yo, Pytorch, my favorite. Yeah, that's what we're doing. You, the engineer, can optimize. Yeah, we sure could. We know how to optimize. If you're the engineer, you can definitely optimize. Mantis, what's the purpose of streaming? You seem to have well-paid position. We're doing it for fun now. We're doing it for fun. Mantis, yeah. We don't need to, we don't need to stream. You're right. Mantis, you got it. Yep. So if you have any questions I'm actually here to let you know what worked for me. What's the project? Kyle, the project, we will be coming up with a project. Right now, we're mostly doing a tutorial. And when I say mostly, I mean completely. We're completely doing a tutorial right now. We're just walking through all the different tensor operations and things like that. Reading through some of the chats here, you guys. I made a typo, meant to say my TV's hungry because it's made in Hungary. Of course it's made in Hungary, and it is hungry. We got it, Brandon, we got it. I appreciate streaming. Kyle, thank you, appreciate you for saying that. It's a really great compliment. One good question, do you prefer Vim or NeoVim? Vim. I like Vim, ordinary Vim. Thanks for the hearts there, I appreciate it. Okay, so we learned about that. Let's run this. Let's see what that looks like. Okay. That should give us ones dot like shape. Do we not have this defined? One's tensor is what we want. Okay, let's fix that. Boop. Okay. I gotta go. Bye. Love you. All right. Brandon, thank you for stopping by. It was good to see you. Enjoyed you having on stream. All right, let's keep going, you guys. Let's keep doing some Pytorch. Okay. Tensors. All right. CPU. Float. All right. This is actually interesting. I like this one. This is great. These are useful debugging things. Thank you for the hearts, you guys. All right. So let's keep going. All right. All right. So this is what allows you to move your... I like this one. This is new. In previous tutorials, they would force you to say a specific accelerator. You could pick one, or you could enumerate all the possible accelerators and then pick one, right? What's great about this one is that you can have it automatically assigned to the most ideal target accelerator. I really like this one. If there is an accelerator, then use it. That's basically what it says. Hey, Roberto, good to see you. Welcome on in. Happy Tuesday. We are going through some Pytorch tutorials. This is great. So let's actually use this now. Let's use it. So let's type it out so we remember it a little bit better. All right, so if torch accelerator is available, okay. If torch.excel, how do we say it? Accelerator.is available, then Tensor, which is going to be something, right? Tensor equals tensor 2. Okay. Oh, really? Okay, so we have to do this. Let's do this. One tensor equals one tensor. This is weird that you have to do it this way. I get it. It's so you're keeping the memory in CPU on the original device, and you're going to be moving or creating a copy onto a new device, and you need to overwrite. So this is called ACC, accelerated one tensor. 2, what do we call it? Torch accelerator, current accelerator. Torch.accelerator.current accelerator, like that. All right, let's try that. And then we will reprint this to make sure it works. Okay. To device, it would just put the best guess it has for the best device. Yeah, that would be nice if it was automatic that way. However, having to do this extra work, the current accelerator. So what you could do is you can just capture this, right? So what you just say, device equals CPU, right? And then what you could do is then you can say device equals the accelerator. Let's confirm that this works. Meanwhile, I have a car accelerator. You're a YouTuber, I'm sure you do. You got a foot pedal. There. Usually what you do is choose device and put it as a global at top. Yeah, exactly. Yeah, there we go. That's kind of what we're doing here. So if we got an accelerator, so let's print this print device. Okay. Let's see if we got one. Yep, right there. It found it, you guys, right there. So that way allows you to easily move to a new device. So you say ones tensor equals ones tensor dot to device. And then you can print. Oh, we just did that. Oh, we already did. We retyped it. No worries. So we print the device, and then we see if it works. All right, let's try it. Let's see if it works. Hey, there it is right there. Perfect. All right, we're looking good. Okay. Continue onward. Let's keep going. Let's keep going, you guys. Let's do some more Pytorch tutorial. So when you move it to the device, what this does is it moves it over to the accelerator. Your system might not have an accelerator. It needs a TPU or a GPU or some sort of embedded ASIC of some sort, right? It could be AMD, it could be NVIDIA, it could be Intel. Intel should work. Or it could be a TPU or an application-specific accelerator. You can have all those. All of them work. Only time you have more than one that Pytorch can actually use if you're doing distributed. Yeah. If you're running on a sort of a cloud server or a giant multi-rack NVIDIA giant server, you can have multiple accelerators, multiple video cards, right? You have multiple, and then you want to distribute your layers across multiple video cards. Or if you're running inference, you could have some of your processes using a different GPU, so that way you can parallelize. That works out really nicely. It's complicated with the sync, is it? You'll print Samsung S26 Ultra. Nice stream, bro. Oh, hey, that's great to hear, YouTuber. Thank you. Appreciate it. I don't think TPU works. It should. TPU only works for Google stuff. It's closed source. Really? Does it not? I feel like it does. Hold on. Pytorch Google TPU support? Question mark. I thought it did. Let's find out. We're learning together. We're learning together. One of us is right. Yes, Pytorch has full support for Google's TPUs. Pytorch XLA library. This integration allows you to run Pytorch models directly on Google's TPUs with only minimal code changes. Hey, there we go. Okay, the image on the canvas is fully rendered. Torva, that was you. All right. Whoa, look at that. That is a scene. Beautiful. You got some cloud coverage here. You got some sort of lake-like item, some sort of lake and a lake shore, and the reflection of the sky. That looks great. Oh, they added a layer like Intel did. They did? Yep, you're right. They're like, Pytorch is a common framework that everyone's using for AI these days. We should probably add the support of our hardware. For years, there was no support. You're right, there was. And there wasn't, Neva. You're absolutely right. Tora, this is beautiful. This is wonderful what you did here. Very nice. I like it. I won't mess it up. I'll just get really close to messing it up. Nope. Oh, we're getting closer. We're getting closer. Oh, okay. Let's see. All right, let's get back to our tutorial, you guys. Let's get through at least more of this page. We should be able to get through most of this. All right, tensor ones. That one's easy. Oh, you can print different columns. We know about this already. Let's just do it anyway. Let's just do this anyways. All right, let's close that. We'll say vi tensors2.py import torch, and then we'll say tensor equals torch.tensor or torch.ones 4x4. Was it a 4x4? Yeah. Print. Well, you're not going to have TPUs unless Google specifically likes you as a person, so how popular Pytorch doesn't really matter. Well, yeah. You can say that. That's for sure. Since they are trying to sell other labs and everyone else is doing Pytorch. That's true. That is true. They've got their own tech. They want you to be on their tech. They sure do. Print tensor. All right, let's see what we got here. Python tensor 2. Okay, so there's our original. You can also print the tensor with just one of the rows, right? You can get one of the rows, I think 0. So that'll be 4 ones, I believe. That'll be 4 ones on the screen when we print that out. 4 ones, yep, there we go. 4 ones, looks good. You can also go the opposite direction, I believe. Wait, what's that going to look like? Nothing. Oh, comma, right. You got to put a comma in there. What's that look like? Curious about that. Yep. So you can do opposite direction. You can also do some extra interesting stuff here. So an ellipses, comma, -1. What does that look like? The same thing. All right, let's go in the opposite direction. Always TensorFlow. Yep, or JAX. Yep, there we go. That's the Google one. That's the Google. I quickly built something. Check in general. All right, Jinla. Normal person equals normal torch. Minecraft equals Minecraft torch. And Python equals Pytorch. YouTuber, we're going to find out. What'd you got in general? CPU usage. Oh, you added system stats. Hey, that's really great. Memory usage, 61%. Storage usage, 83%. Wow, you've got a lot of storage that's used. What do you got on your system that's that much, almost a terabyte? Wow. I get the CPU usage because you're running a game, right? Memory, aren't you running Bedrock? So that's actually pretty good. That's a lot of RAM. Very nice. I like how you got system stats on there. That's awesome. All right, let's keep going. La 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 la. Okay. Oh, you can set. I like this. This is neat. I like how you can do this. If you want to manipulate part of one of the columns or rows, you can do that with the tensor. This is really neat. All right, let's try this. So we'll just regular print tensor. And then we will set the tensor at, what was that? Comma 1, row 1. Let's do row 0, just to mix it up. We'll set it to all zeros. Then we reprint it. And we should see, I believe, the left column, right? The left column should all be zeros. The left column. It's all Minecraft memes. It is. It's all the Minecraft memes. That's 1 terabyte of Minecraft memes. Using HTML and Python program to send stuff to PubNub and a website to receive it. Genlu. Oh, I get what you're, oh, very nice. Okay. That's a good way to do it. So you can get your actual data from your system into the Minecraft world. You can see a web page. You can see the output there. So you can you run a system stat on your local system, obviously running Minecraft at the same time. And you can import that data and have it displayed in Minecraft using PubNub. I like it, Jinlu. That's amazing. Could be worse. At one point, your app data reported itself to be 650 gigabytes when you fixed it. Nice. Don't know why you're using so much storage. Well, let's see if this works. Oh, did we type that wrong? Oh, we sure did. We typoed that really good. Ones. Okay. Yeah, there we go. The left column fully. There you go. Right there. You should see a column if you do this. Colon? Just a regular colon? Or if we just do colon? Really? All right, let's try it. Bracket, colon, bracket. Is that going to work? Didn't quite do what I thought it was going to do. 1. We get row. Let's try 1, this. This would be the same thing. Okay. Oh, good. Oh, that makes sense. Hey, Alex Pro Gaming, thank you for subscribing. Appreciate it. Good to have you here. You joined the right channel for software engineering. Or, never mind, misspelled it. Oh, hey, no worries. No worries. We're going through the Pytorch tutorials right now. And it'd be nice to get through partway. So we have a few minutes left. We're not done yet. Let's do a couple more of these lines to understand. So we did the concat. The concat is easy. The concat will... Let's change the dimensions and see what that looks like. Print. We'll do print tensor. Concat. Just cat, right? Torch cat. Torch.cat. Tensor. Like that. And we'll see what it does default. We'll see what it looks like by default. I'm actually kind of curious about that. Okay. It needs to have a dimension. Oh, it's got to be an array. Okay. So let's see what the default dimension is. Okay, so it stacks it. So it's going to concatenate it like it's a bunch of batches. However, if you change the dimension, dim equals 1, it will turn, instead of concatenating it downward, it'll concatenate it out. So you add more columns instead of adding more rows. Like these type of YouTube. You're chill. I like it. Oh, that's great to hear. Thank you. Appreciate it. That's good feedback. Thank you. We're gonna keep going. We're gonna keep going with the ideas. Yeah, I like these too because we just walk through the tutorial. We sort of see what each thing does, and it allows us to hit maybe some mistakes, which allows us to memorize a little bit of what we're doing. A little bit of what we're doing. Let's add another 4 columns by saying tensor. So that add 4 more columns. There you go. 4 more columns right there. 1, 2, 3, 4. 4 additional columns. All right. Let's do a couple more. The arithmetic. So now we're getting into what Neva did for our tutorial previously when we were doing this earlier this year. Was it earlier this year or was it last year? I feel like it was maybe in January. So we can do a matrix multiplication. Let's do that. Let's comment these out. All right, so let's do it. Let's do print tensor at matrix multiplication tensor. And we don't have to transpose it. We don't have to transpose it because it's identical, right? You would have to transpose it if you had the need to. You don't need to in this case. Yep. So that did a matrix multiplication, which combined the 2 tensors together. What happens if we do another one? Can we do that? So it's going to be even a bigger number now. 16. Oh, let's do it again. Will this go to 32 or 64? At tensor. Okay. So for those of you who are here, let's see if we can figure out, is the answer, is this going to be 32 or 64? Let's copy paste that. All right. Start a poll. Will this be, what was it here? 1 second. Let me look back at our answer here. Will this be a bunch of 6? The answer is 32s. Or will it be 64s? Or will it be 128s? Which one will it be? Let's see if you can find out. I don't know. I'm not sure. I feel like it could be 32 or 64. It could be between those. I'm not actually sure for sure. We're going to find out. I'm so busy. Got to go. Bye. All right, Kyle. It was good to have you here. Appreciate it. Thanks for stopping by. Not sure why I just did what I did. You put a screenshot in general? All right, let's take a peek. Whoa! So is this a skybox? Or what is it? Is this a block? What did you do? Is this a whole bunch of different... It looks like different screens. I see you're doing the web page there. That's really neat. It looks like a skybox. However, I believe since you're like right at the corner of one, it looks more like a block. And you're looking inside the block? Or you're in a room with a bunch of blocks? How'd you do this? How'd you do that, Jinlu? Technically for cache, locality is better to transpose. Is it? In multiplication, like storing it, transpose it better? Really? So it's faster? How? Well, I suppose it doesn't really matter because you're still accessing the elements independently, and it doesn't matter whether you transpose or not. I feel like it would be identical, right? I feel like it's the same thing. It's a web browser display in a cube with all the PubNub website. Hey, nice, Jinlu, thank you. That's fantastic. All right, we're gonna find out. Is this gonna be? So you saw. So this is gonna be 16. This will be 4. So that's 4, 16, and then 32 or 64. I feel like 64 is gonna be the answer. You guys think it's 64? Okay, let's try it. Save, run. Here we go. It's 64. Good job, you guys. You picked the right one. It was a bunch of 64s. Accessing on the not 0 index means you're jumping in instead of +1. So is there an extra addition you're saying? I feel like you're just iterating through the elements. And it's the same number of iterations either time, right? It's the same number of iterations whether you transpose or not. The transposition is just saying what dimensions you're supporting first. Cache likes smaller jumps. Oh, okay. I'm somewhat... so, when the numbers are closer together? I don't... What do you mean? If the cache is in... If the memory, the address of the cache, I feel like it's going to be the same speed. So, are you telling me... So, all right. Neva, if I run this in a for loop, are you telling me that we're going to see the tensor torch? I'm not sure. Yes, it's a complexity, but it's closer in memory. So if we put a for loop and we run this, would you be confident in saying that running a transpose would be faster? Or would it be the same? So let's do this. All right. Import date time. This will be the last thing we do and we have to head out. So we're going to do a quick little benchmark. You need a matrix that doesn't all fit in one cache line. Like it needs to be big. Oh. Well, in that case, yeah. All right. Well, okay. So we don't need to worry about it then. So it's more optimal due to hardware restraints. Oh, yeah. If it's big and it can't fit all into the same cache, then got it. Okay. If you make a large enough matrix and measure correctly, it would be. I'm learning JavaScript right now. All right. JavaScript's a great programming language. We're doing some Python here. Thank you for hanging out with us. Even though you're doing JavaScript and we're doing Python, I appreciate it. Got it. So if we make a really big one, how big does it have to be? How big does it really have to be? Like 4,000 by 4,000? Is that too big? Will that cause explosions? Do I have enough memory? I don't have enough memory. Oh, we'll have to do it. We'll have to try it later. We'll try it later. Okay. All right, you guys. Let's do... It's your first language? Nice! JavaScript. JavaScript's a really good language. As a first language, you did a good choice. I would say JavaScript and Python are excellent first languages. All right, you guys, let's do a little bit more and then I got to head out. Let's do some torch ran like mult out Z3. Oh, look at that. Okay. So you can override it. This is neat. I didn't know you could do that. I didn't know you could do out. That's pretty neat. Okay. So let's do this. We'll do this last bit here. We'll use the mult, the mult, and then we're gonna head out. Not that big, like a cache line OS. Oh, so 1,000 by 1,000 depends on size. Okay. All right, Neva. All right. Let's try it out. All right. So we don't need it. Doesn't need to be that big. 1,000 by 1,000. All right. Let's try it. We're gonna try it. We're gonna do it. We're doing some benchmarking now, you guys. Here we go. Import date time. And then we say, what is this? Python import date time. Date time dot now. It's now not doesn't exist. Or date time dot time. Like that. Can we convert that to an integer? No, doesn't like that. Float. Doesn't like that either. How do we get now? How do we get right now? This exact moment. We could look this up. We could totally look this up. All right, time. Here we go. Min max is there now? Resolution hour. Fold minutes. Is there like I want the current time. I want the current time. Hey, ICANN-R, how's it going there? How many memory do you have? We got a lot of memory. We're going good. Planning on getting an internship next year. Do you have any advice on me? Someone who has no industry experience. Yeah, you want for an internship, you have to just apply everywhere. Just apply everywhere. Apply. Be very, very generous with your applications. Apply everywhere and then measure. Yes, we're gonna do it. And a good measurement. So first loop and get the CPU hot, and then code, decode, and in cache. Okay, we're gonna try it. Have a beautiful day. Fun stream. Sergio, thank you for hanging out. I appreciate it. All right, Neva, we're gonna do some benchmarking here. Let's do it, and then we're gonna head out. That'll be the last thing we do today. We're not done yet. We're not done yet. All right, date, time, Python, current, now. Yes, I need the exact moment. How do we do this? I forgot Python. You have to do this. That's really annoying. Okay, from date time, import date time dot now. Oh, can we do? Okay, date time. What if we did? Here, let's close this. Redo this. All right, import date time dot now. There we go. Okay, that's what I like. Okay, so let's do benchmark. How do we do this? Def start. Start equals date time dot now. We're just gonna keep it simple. Okay. Okay. Have a measure it. You're measuring it yourself too. All right, sounds good. We're gonna run into see how it works together. All right, so we go start. Okay. MV tensor 2, CP tensor 2 to bench pi. Okay. Tensor start. Then we'll do a for I in range 1000. See if that's enough. We will do the first one. This will be transposed. Not transposed. Print not transposed. This is gonna be great. I'm really excited about this. Again, Steve, you have to run on a loop frost and not measure it. What? So you want it to run first, so you do an initial run, and then you test it again, and then you test it again. All right, Never. All right, we're going to follow your instructions, and we're going to find out if this is really the way it is. All right, we're going to find out. This is going to be great. Or it predicts it's going to always be a second you measure it. Hey, Face Cam, good to see you. Hello. All right, Neville, let's build it. Let's build it. Yeah, We'll do the start. So we got the start here. Tensor at tensor dot transpose. All right, nothing equals. Okay, then we say end print latency, f string, latency equals the end start, end minus start. Okay, that should do the trick. I think. If you don't do that first unmeasured, then A would have a cold CPU. So what we'll do is we'll do this. Okay, so we'll do it unmeasured. Here we go. Warm up. So we'll say warm up. Warm up. There we go. Warm up. There you go. You got warm up there. Then we've got the actual starting. Warming up. We're following your instructions. Is what we're doing. Are the demo keys in PubNub is free forever? Yes. Free forever. Free forever. They're not secure though, so if you need security, you got to get your own API keys. They are free forever though. Obviously, someone could like find your data channel and consume your data, so be careful. Be careful. All right, let's benchmark you guys, and then we'll head out. We're not done yet though. We're not done yet. Okay. Close that. Okay. So this is the transposed, and then we're gonna do the same thing. Starting non-transposed test first. Okay. How's it going there, Norma? Welcome on in, ChatGPT 5, OpenAI, DigiArt, Artificial Intelligence. I just used demo keys for my CPU thing. Oh, nice, Jinlu. Excellent. You're on the right track. Seems like my machine 1,000 by 1,000 is negligible. Okay, we gotta bump it up then, right? We gotta bump it up. It fits nicely into the L1 cache. Are the channels have maximum characters? Yes, they are. So you a lot though. The maximum size, you can go up to like 30,000 characters if you want. Don't do it. You can. You don't want to though. There's no need. I would say like maybe 100 characters is safe. If you do 100 characters, you can do 1,000 characters. If you really want to, you can do 1,000 characters. You can do 10,000 characters. You could do 20,000. You could do 30,000. It's not necessary to do that though. It'd be wasteful. Nobody can really do anything with my CPU memory and storage usage anyways. Jinlu, you've got compute there. You've got compute. All right, warming up. Not transpose, starting non-transpose test first. Okay. And then we're going to do the other test here. We're doing the transpose test. Starting transpose test. Okay. Let's get rid of this. Just keep it nice and tidy. Dot transpose. Dot T. That's it right there. All right, let's see if we get the same results as Neva. Neva, I'm mostly calling you out because I think this is weird. I'm like, it's just a transposition. It's the same data. Warming up, starting. Okay. Yeah, it's about the same so far with 1,000 by 1,000. So what we can do is we can bump it up. We can bump it up a little bit more. And it looks identical. They're essentially identical. Identical for the most part. The non-transposed test seems to be just a little bit faster for some reason. I wonder why that is. I wonder why that is. Well, yeah, it's compute. You really not do much with the usage of the information. Only made possible to run commands through PubNub, but right. Yeah. Hey, yeah. No, you're good. Your data is fine. There's nothing to worry about. You didn't expose anything. You're transposing the wrong one. Oh, really? Okay, we'll do the other one then. All right, we'll do the other one. Here. All right. There, the first one's transposed now. Is that better? All right, warming up. Oh, hey, that was a little bit faster. All right, let's try again. Oh, it is. What? No, LHS should be transposed. LHS, what are you guys doing? Hey, Garcia, welcome on in. Neva has been describing that the transposition when doing a matrix multiplication is going to be faster. And it kind of looks like it is a little bit. Yeah, it is. Neva, good job. You win? You win, Neva. I should have assumed that you won. I should have won. You should have. You shot. All right, let's bump this up. Let's go a little bit more. Let's double this. Nah, Neva. Good job, Neva. All right, let's try again. Let's double check. Let's actually run a little bit more. 1.2. Oh, yep, you're right. Look at that. It's a whole 100 milliseconds faster, which is necessary. That is, especially when you're doing a lot of these all at once in the big world, when you're doing AI training, milliseconds count. Neva, you win. Congratulations, Neva. Good job. We should have made a poll out of that. Bet Pytorch does something similar. Yeah. Like if it was untransposed, it would automatically be transposed. It's possible to see available channel or active channel just for caution. No, it is not. It's not possible. You'd have to scan. You'd have to scan for it. So Facecam, if you're looking to, and Jinlu as well, if you're looking to add some security into it, you need to create a long channel that's non-deterministic. A long random channel name that is unguessable. Essentially like how API keys work, right? So if you make a channel name that's over 100 characters random, 100 characters random, you're good. You're good. No one's going to be able to guess that. They're not going to be able to guess it. So you're good to go. You're good to go. Neva, this was great. Thank you. You taught me so. I'm like, there's no way. There's no way. But you were right. You're right. Let's make this a little bit bigger. Let's double it up. Let's go double. 2,000 by 2,000. All right, let's try to warm up. Let's warm up here. Let's see if it gets into the range. Should take roughly 4 times as long. Or longer, maybe 8. Yeah, okay, there it goes. Starting non-transposition test. Neva, thank you. making Python compiled. It's going great. Oh, really? Compiled. Really? How did you learn TensorFlow? Oh, Garcia. Well, mostly when it came out, I messed around with it, and then I got into Keras, TensorFlow Keras. What we're doing here, though, Garcia, is we're using Pytorch. Never look at that. This is a whole 2 seconds faster. That is, although, hold on. I'm actually kind of curious. What if we change the order? It's probably, so will this one be faster? We're just gonna try it out. Okay. All right, last thing we do before we go, you guys. Start. I'm gonna do a quick poll. If we change the order, will it change outcome? Here, I'll describe what we're doing here. So we are running a test on matrix multiplications. We are testing transpositions and non-transpositions. If we change the order, which we just did, right? So if we started with non-transposition, it took longer. If we changed it, and then you see the transposed was 2 seconds faster, right? However, if we switch the order, will the same results occur, or will it not? Will it be identical? So basically the idea is, will changing the order make a difference? We're gonna find out right now. It takes about 40 seconds to go. There it goes. All right, we're gonna find out in 40 seconds. What are we doing here? Hey, how's it going there? Off. We are doing some benchmarking, you guys. Hey, Claude here. Good to see you, Claude. If we look at the source code for the linear layer, we would see that it's using this. Is it? Okay, so it's already doing it automatically. Hey, it order changing. It looks like it didn't matter. It didn't matter. Never. Thank you. You helped us learn something new today. You like transpositions? Well, you should, because they make things faster. Only remember that if the matrix is diagonal. Ah, all right. Well, in our case, the matrix is a square. It's a nice big square. All right, you guys. I had a lot of fun today. The answer, by the way, to the poll was it didn't matter. It doesn't matter. Changing the order doesn't matter. As you can see, it works perfectly nice. Either direction. Either direction, you guys. All right. Thank you, everyone, for joining. I'm headed out now. Had a good stream today. I enjoyed it. We'll be back tomorrow with more Pytorch. We'll be doing some more Pytorch tomorrow. Okay, one last funny thing for today in general. Oh, Jinlu, okay. Just one more thing. Check in general. Okay. Sometime change the order. See, like, yeah. It seems like it. Sometimes it does, sometimes it doesn't. It's just always correct because the transposed version does a x0, x1, x2. So it's order. Hey, how's it going there? Noon. I thought most coders don't care about optimizing code. They only care if it works? We like optimal. I like optimal. I like speed. That's why my company, you guys, speed. The other does x. Oh, okay. X2000, X4000. Got it. So it's just I kind of get it. Not really. I kind of get it. I'm just glad that we know now. We know. We'll remember. And so X0 and X2000 are not the same in cache line. Got it. Okay. Xfinity order possible. All right, Jinlu, let's check out the what do you got here? What's going on? Are you doing a terminal window? Wait. That's a terminal window. Oh, you're booting. Wait. Oh, that's from Aperture Science. Okay, is this? I got it. Okay, this is GLaDOS. This is GLaDOS. This is GLaDOS in. Was it Portal? In Portal. Hey, that's pretty neat. Wait, Torva, wait. Okay. Torva, I'm not a bot. Claude here. Wait. That's neat, Jinlu. It's a virtual machine. Is it? That's pretty neat. Jinlu, I like what you're doing here. No way! Is it? Are you running Linux or something? I'm human, bro. That's really neat. You got Neva excited. Someone turned the portal credits into an operating system. Oh, what? No way, really? The portal credits. It's actually its own operating system. Wow. What do you know? We're learning all sorts of new, weird, fun things every day. New things every day, you guys. It's a huge success. I know, right? That is great. That's just amazing. It's unexpected. Okay, you guys, I'm headed out now. I had so much fun with you today. We'll be back tomorrow with more Pytorch. We'll be doing some more tutorials, and eventually we'll get to a project. Neva, if you have any ideas, let me know. Some fun projects we could do. Happy to get things going. So someone made a completely new kernel just for the meme. Yeah, they did. Just for the meme. That's great. That's awesome. It's ridiculous. I know it is. Yeah, absolutely ridiculous. It is. All right, you guys. Thank you so much for joining. I got to head out now. It's ridiculous and it's fun. Yeah, you got it. I'm really a mod. Chat. Claude. Oh, wow. Okay. All right, you guys. Thank you so much for joining. I had a lot of fun. Oh, I didn't know you changed your name. Yeah. You changed your name. It has audio too. That is really neat. Still alive. It's been a pleasure to see you all tomorrow. Thank you, everyone. We'll be back tomorrow, you guys. It's good to see you. We'll be back. More Pytorch tomorrow, you guys. Thank you, everyone. Had a lot of fun. See you tomorrow.